Hi everybody, this is Mrs. J, and today we're going to start our review, and we're going to start off with some trigonometry review. Alright, so I have a quick warm-up for you guys to try, so please pause the video and hit play when you're ready to check your work. Alright, go ahead and check your work here. So you can see for each of these, I found a more manageable coterminal angle to evaluate. And for part A, since it's cosecant, I actually evaluated using sine. So the sine of pi over 3 is root 3 over 2, and then I did the reciprocal of that because cosecant's the reciprocal of sine. For part B, I used, again, negative 3 pi over 4. So this is in quadrant 3, and the reference angle is pi over 4. So my answer must be negative root 2 over 2. And also remember this little trick, ASTC. This tells you what is positive in each quadrant, which I know my answer is negative in quadrant 3. And then for part C, here I used pi as the coterminal angle. So the tangent of pi is 0, so the reciprocal of 0 is undefined. So cotangent of pi is undefined. Or if you remember what the graph of cotangent looks like, you remember there's actually a vertical asymptote at pi. Okay, so we are going to start by reviewing all of the graphs of our 6 trigonometric functions. So here you can see I have the parent functions first for sine, cosine, cosecant, and secant, and then we'll look at tangent and cotangent next. So a few important things to remember. For sine and cosine, we have these wave-shaped graphs. I always say that sine for the parent function starts at the origin, and I say that cosine starts at the maximum. And then both of these graphs have a period of 2 pi and an amplitude of 1 for the parent function. And of course, we can transform them, so that could change. But again, this is just what our parent function looks like. And you can see that they are really the same graph, just shifted over by pi over 2. And then if you look down at cosecant and secant, I put these right beneath for a reason, because we can actually use the graphs of sine and cosine to help us find these graphs. So remember, since cosecant is the reciprocal of sine, wherever sine is 0, cosecant will be undefined because the reciprocal of 0 is undefined. So I look at my midline of this graph, and everywhere that it's 0, so you can see that that'd be here, 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 here. Notice that we have a vertical asymptote for cosecant. And then also I take some really nice, easy values, which would be like pi over 2, 1, 3 pi over 2, negative 1. And we can actually use those as points for our cosecant graph, because the reciprocal of 1 is 1 and the reciprocal of negative 1 is negative 1. So you can really just take the hills and the valleys of your sine graph and you kind of just flip it over, and they make these little mini parabolas that are bound between each of your asymptotes. So the period of cosecant and secant is 2 pi. You can see here I have the repeating asymptote equation where n represents any integer. So you can see that the vertical asymptotes are repeating every pi units. Our domain is going to be all real numbers except for those asymptotes. And then you can see our range is everything except the stuff in between negative 1 and 1. So negative infinity to negative 1, and then 1 to infinity. You can find secant or graph secant in the same way that we did cosecant. So remember, since it is the reciprocal of cosine, wherever cosine is 0, which should occur here at these points, notice we have vertical asymptotes for secant because the reciprocal of 0 is undefined. And then anywhere where our value is 1 or negative 1, I use those points for secant because the reciprocal of 1 is 1. And again, it makes those little mini parabolas within each asymptote. So again, same period. Here you could see that our asymptote equations are a little different. Remember, we just named one. So we have pi over 2, and then it repeats every pi units. Domain and range, very similar to cosecant, except, again, it's everything except for our asymptotes. So those are a little different, but same general idea. Now for tangent and cotangent, let's start with tangent. So if you take some points, from around the unit circle, and you plot them, you end up with a graph that looks like this. So tangent does have a vertical asymptote every pi units. Notice that the period of tangent is just pi, not 2 pi like our previous graphs, just because tangent doesn't take as long to start repeating itself. So our asymptotes are going to be at pi over 2 and negative pi over 2, and then it's just going to repeat every pi unit. So I said plus pi n. Notice that we're centered around our y-axis for these. And then I always like to kind of start with the points 0, 0. This is pi over 4, 1, and negative pi over 4, negative 1. And so we have these nice 3 points, and it will kind of approach our asymptotes to the left and right in each boundary. So here again, you can see I have this repeating asymptote equation. Again, they repeat every pi units. And our domain is restricted to include everything except for those asymptotes. And our range is going to be all real numbers. For cotangent, it looks very similar, but kind of similar to how we did secant and cosecant. Wherever tangent is 0, cotangent is going to be undefined because the reciprocal of 0 is undefined. And so we have asymptotes still every pi units, but they occur at 0, pi, 2 pi, so on and so forth. So you can describe those asymptotes with this equation. And you can see that within each boundary, we kind of have this negative graph, or not negative, sorry, decreasing graph. And I like to use the same key points. Here we have pi over 4, 1, pi over 2, 0, and then here we have 3 pi over 4, negative 1. And you can kind of repeat that pattern in each boundary. So for cotangent, I like to say that we kind of, instead of being centered around the y-axis, we kind of start with one vertical asymptote on the y-axis, and then we can find the next one according to the period. Of course, that could change if we have a horizontal translation, but that's a good starting point when you're graphing cotangent. So now we're going to try to graph a few of these together with some transformations. So we're going to start with a nice cosine graph. So here you might notice that we have this b value of pi. So here we do need to factor this out before we evaluate what's going on in terms of transformation. So again, remember, whenever you have a horizontal stretch or shrink, it needs to be factored out so it's separate from any horizontal translation. So that's the first thing I'm going to do. So I'm actually going to write my equation over here. So again, I'm going to factor out the pi. It's still going to remain within my cosine function, but then it's going to look like this. So if you didn't do this, you might say, okay, my graph is shifting to the right pi units, but you can see it's actually only shifting to the right 1. So when I'm graphing cosine or sine, I kind of have this process that I follow. You can do it differently, but here's what I recommend. I like to start by finding the period. So remember the period formula, it's 2 pi divided by whatever b value you see here, but really we're just multiplying by the reciprocal of this factor. So the period is 2 pi times 1 over pi, so our period is 2. So just a tip in terms of scaling your x-axis, I always like to take the period and split it into 4. And that's usually a really good way to scale your x-axis. It's not always perfect, but it's usually pretty good. So I'm actually going to scale my x-axis by 1/2 of a unit. So now that I know my period, I'm going to try to find the midline of our graph. So here I can see that our graph is actually shifted up 3 units. I'm actually just going to extend my graph just a little bit. So I like to actually sketch in a little dotted midline here. So now instead of our midline being at y equals 0, our midline is at y equals 3. And then I can look at the a value to find the amplitude of our graph. So our amplitude here is 2. Remember, amplitude is always positive. This negative is a different transformation. So that means that from my midline, if I go up 2 units or down 2 units, I will have my maximum and minimum values. So it looks like this. So I like to just sketch those in as kind of guidelines for the rest of my graph. So now I like to find what's called the starting point. So we have to do a few things here. So cosine, I always say, starts at the maximum. So usually it would start here. However, we do have a reflection, so that brings us down to the minimum. So we start at the minimum. And I also see that we have shifted to the right 1 unit. So I'm going to shift my starting point to the right 1 unit. And I call it a starting point. Really, there's no real starting or end point of cosine or sine. But I'm going to shift my quote unquote starting point here. And then once I have my starting point, I know that the distance from the minimum to the midline is going to be 1/4 of my period. And I've already scaled my x-axis accordingly. So now I just kind of follow the scale of my x-axis and I follow the pattern. I jump to the midline and then to the maximum and then back to the midline. And I can continue this pattern going to the left as well. So midline, maximum, midline, minimum, midline, maximum, midline. So I can continue the pattern as far as I want to go. And then from there, all we need to do is connect the dots. And there you have it. So again, this is just kind of one approach to graphing sine and cosine, but if you have a different way that you prefer to graph, that is totally fine. Okay, let's try another one together. So here we're going to be graphing cosecant. So whenever we graph cosecant, I actually like to first graph its reciprocal function, which in this case is sine, applying the same exact transformations in our new function or in our original function. And I kind of use this as a guideline to help me graph cosecant. So if I'm graphing this sine graph, first if I find the period, again we take 2 pi and I multiply it by the reciprocal of this b value. So I'm actually going to multiply it by 2. So our period is 4 pi. So I'm going to scale my x-axis by pi. Again, I like to take my period and divide it by 4 to kind of hit the 4 quadrants of our graph. And then I see that our amplitude is 1/2. And I also see that our graph has shifted down 1. So I'm going to actually set the scale of my y-axis to 1/2 just to make it a little bit easier to graph. So since our graph has been shifted down 1, that means our midline is at -1. And then I go up 1/2 a unit for our maximum and down 1/2 a unit for our minimum. And then I always say that sine starts at the midline. So in this case, it's there's no shifts left or right. So it's going to start here at the midline. So this is kind of a little starting point right here. And then I'm just going, there's no reflection. So I'm just going to start by going up to the maximum. So here, and then middle, minimum, middle, max. And I kind of just continue this pattern as far as I can. And again, I'm just doing it as a dotted line because this is just a guideline to help us graph cosecant. So now I have this guideline, we can actually start graphing cosecant. So first thing I always like to do is I like to graph my vertical asymptotes. So remember, the vertical asymptotes are going to occur whenever our sine graph was 0. So for this, we're actually going to look to our midline. So wherever it's crossing our midline, that's where we're going to have a vertical asymptote. Because usually we would see where it's crossing the x-axis, but remember we do have that shift down. So I'm going to look at our midline, and anywhere we have our midline is equal, or our graph crosses our midline, we're going to have a vertical asymptote. Like this. And then from here, the rest is pretty quick and easy. I'm actually going to take any hill or valley, and it becomes kind of the vertex of our little mini parabolas within each region. And then it just follows along our asymptotes, going up or down. Yes. And there you have it. It is sometimes useful to list out those repeating asymptotes here. So in this case, our asymptotes, well, I see that we have one at 0. Again, you can start by naming any asymptote. I'll just say 0. And then it's going to occur again every 2 pi units. So you can see there's one at 2 pi, then 4 pi. So we can describe that repeating pattern by saying plus 2 pi n. Remember where n is any integer. So this would essentially add any multiple of 2 pi, and since it's an integer, that would cover the positive and negative direction. So that's about everything we would need for our cosecant graph. So remember, for cosecant or secant, I'd like to start by graphing the sine or cosine graph with the same transformations in our function. All right, and last, we're going to try to graph a tangent function together. So first thing to notice, again, we have that b value here, so we do need to make sure we factor that out. And I'm also going to move this to the back. It is still just a shift up 2, and I know it looks a little bit different, but you can write that 2 wherever you want. So I like to just put it at the end, but you can leave it out front as well. So again, I'm going to factor out the 2, so I have x plus pi over 2 plus 2. So first we can start by looking at our period. So the period of our parent function is pi, remember, and then I'm going to multiply by the reciprocal of our b value. So this is actually a horizontal shrink by a factor of 1/2. So now our period is pi over 2. And just like when I'm graphing my other functions, I like to take this and I like to split it up into 4 to scale my x-axis. So I'm actually going to scale my x-axis by pi over 8. So the next thing I like to do is I like to place the vertical asymptotes. So typically, again, tangent is centered around your y-axis. So you would typically have 1/2 of your period to the right and 1/2 of your period to the left, which in this case would be pi over 4 to the right and pi over 4 to the left. However, our graph is also shifted to the left pi over 2. So this is left pi over 2. So instead of having a vertical asymptote at pi over 4, if you shift that to the left by pi over 2, it actually brings us here to negative pi over 4. And then again, that's going to repeat every pi over 2 units, which would be 4 tick marks. So when you have a shift that is the same distance as your period, it's actually essentially doing nothing to your graph. You're going to end up with the same exact graph as the equation without the same shift. So again, if the shift and the period match, it really doesn't change your graph at all. And we can kind of continue this pattern of our asymptotes, just 4 more tick marks to the right or left. You can add in an extra tick mark if you'd like. So it looks like this. Okay, and then tangent is always going to have a point right in the middle of your 2 asymptotes. Usually it would be here at the origin. However, we do have that vertical shift up 2, so it's going to be right here. And then it's also going to have our quarter way points. So typically from wherever the midway point is, you would go up 1 unit and then down 1 unit. However, we do have a vertical stretch by a factor of 2. So for the quarter way point here, we're actually going to go up 2 units here, and then back, and on the other side for our quarter way point, we'd go down 2 units. So it looks something like this. And we can kind of repeat that same pattern within each boundary of asymptotes. And we can do one more period here. So again, notice, again, this distance, this vertical distance from your midway point to your quarter way points is always going to be whatever this a value is. And if there's a negative out front, so if there's a vertical reflection, then our graph would be decreasing, so it actually ends up looking more like a cotangent graph than a tangent graph. Oh, and the last thing we can do is we could describe our repeating asymptote. So we do have an asymptote at pi over 4, and it's going to repeat every period, once every period. So we say plus pi over 2n. So that's our repeating asymptote equation. All right, so now we're going to do a quick review of our inverse trig functions. So we know for sine, cosine, and tangent, the input into the function is an angle, and the output is a value. For example, we say sine of pi over 6 equals 1/2. So the input's an angle, the output's a value. For the inverse trig functions, arcsine, arccosine, and arctangent, the input and the output are swapped, right? Because everything about your inverse function, the x and the y's, the domain and range, input and output are always swapped. So notice in this case, the input is the value, like you would say arcsine of 1/2, and then the output is an angle. So you'd say is pi over 6. So here's the thing with our inverse trig functions. You have to look to the original function. For a function to have an inverse function, it must be a one-to-one function, which means it passes that horizontal line test. However, if you think about sine, cosine, and tangent, they all fail the horizontal line test. So their inverses would inherently not be a function. So what we need to do is we actually need to restrict the domain of our function to ensure that the inverse is also a function. So for sine, notice, look at this tiny little chunk of our graph that we took. We're actually going to limit the domain to negative pi over 2 and pi over 2. So we're only taking this one piece of our sine function to help us find our arcsine function. Cosine, the domain is limited to between 0 and pi. And then tangent is just limited between negative pi over 2 and pi over 2. Notice for these two, the boundaries are included, but for tangent, they are not, because of course this is where we have asymptotes. So I like to always just remember, for sine, we're kind of going from a minimum to a maximum, and we're kind of just try to center it as much as possible. And for cosine, we're just going from a maximum to a minimum. So you are making sure that we include all of the possible values within the restricted domain without violating our horizontal line test. So since we had those domain restrictions to our original functions, that would result in range restrictions for our inverse trig functions. So notice that the range of arcsine is negative pi over 2 to pi over 2, which was the restricted domain of our original function. The range of arccosine is 0 to pi, and the range of arctangent is negative pi over 2 to pi over 2. For our domain, the domain of arcsine and arccosine was the range of our original function, which is negative 1 to 1. So for these, you can always just ask yourself, what's the range of sine and cosine? That becomes the domain of arcsine and arccosine, because again, remember, domain and range are swapped for the inverse function. And then the domain of arctangent is all real numbers. So what does this mean? So the domain, of course, tells you what we can actually plug into the function, right? That's our input. So this is our input. So technically, we can only plug in a number for arcsine and arccosine that's between negative 1 and positive 1. So if in your calculator you try to do like the arcsine of negative 2, your calculator would say undefined. That does not exist for this function. But for arctangent, this is essentially telling us we could plug in any number into arctangent and we will get an output. Now, the range, or the output, again, tells us what our answer will be. And again, for these, the output is an angle. So this is telling us that for arcsine, if we use arcsine, it can only give us an answer between negative pi over 2 and positive pi over 2. So if you think about where that is, for arcsine, it's only going to give us an answer, some angle, again, from negative pi over 2 to positive pi over 2. So it will never give you an angle in quadrant 2 or 3. Again, it will never give you an angle larger or smaller than pi over 2 or negative pi over 2. And then for arccosine, since the range or the output is 0 to pi, it will always give us an answer, some angle in quadrant 1 or 2, a positive angle in quadrant 1 or 2 between 0 and pi. So just kind of look at the pictures here and just try to remember where your answers will be. So you'll never say that the arccosine of some value is, 3 pi over 2. It will always be between 0 and pi. And then for tangent, it's going to give us our answer, or our output will be some angle again between negative pi over 2 and pi over 2, but this time not including those two. So for these, they are included, and then for these, it is not. Okay, so just remember that when you're evaluating an inverse trig function, the answers that the output, or the answers that you get, can only be in very specific quadrants, depending on which inverse trig function you're working with. All right, so now we're going to try to evaluate some expressions that have inverse trig functions in here. So here we have the sine of the arc sine of 1/2. So for this, we always kind of start on the inside and work our way out. So let's start with the arc sine of 1/2. So again, it's extremely important that you understand the domain and range of all of your inverse trig functions. So I know that this is within the domain, and our range, again, if I like to kind of visualize it like this, the range of arc sine is negative pi over 2 to pi over 2. So we want the angle whose sine is 1/2, positive 1/2. So that must be pi over 6, because the sine of pi over 6 is positive 1/2. And then here, now that we know that the arc sine of 1/2 is pi over 6, we just do the sine of pi over 6, which is 1/2. So you'll see here that we have the sine of the inverse. So since it's the original function and its inverse, they kind of canceled each other out. All right, let's try this next one. So let's start on the inside here. So the tangent of 0. So the tangent of 0 is just 0. So then we're going to find the arctangent of 0. So remember, for arctangent, our answer is going to be between negative pi over 2 and pi over 2. So the angle whose tangent is 0 is also 0. Remember, this is 0 radians. Our answer here is an angle. I know it's difficult to tell if it's an angle or a value, but this is 0 radians. All right, let's look at part C. So we have the arc cosine of the cosine of 7 pi over 6. So let's start on the inside. So here, 7 pi over 6, so this is in quadrant 3. So our answer is going to be negative. And the cosine of pi over 6, which is the reference angle, is root 3 over 2. So now we want to evaluate the arc cosine of negative root 3 over 2. So remember, for arc cosine, the range, which is the output, is going to be some angle between 0 and pi. So since our answer is negative, or the value is negative, that means that our angle is actually going to be over here in quadrant 2. So in quadrant 1, cosine is positive. So I'm saying which angle has a the cosine of which angle is negative root 3 over 2, and that would be 5 pi over 6. So you have to be careful whenever you have a function and its inverse, like you had in part A, you can't always just assume that you can cancel them out and your answer is whatever this value is, because in this case, the angle here was in quadrant 3, but the range of our cosine is between 0 and pi. So we actually have to have an answer that's in quadrant 2. But notice both of these angles do have the same reference angle. All right, let's try one more together. So here we have the sine of the arc sine of 3 over 2. So if you start on the middle, or on the inside, you might notice something right off the bat, hopefully. 3 over 2 is greater than 1. Remember, the domain of arc sine and arc cosine is between negative 1 and 1. So this is actually undefined. All right, we're going to try two more together. But here you're going to notice that we're actually not working with unit circle values, but we can still evaluate them using what we know about our inverse trig functions. So here we have the tangent of the arc sine of 1/5. So remember, when we see this, this is just saying the angle whose sine is 1/5. So to help us visualize this, let's actually sketch this out. Let's give ourselves a little axis. So we know that this angle, since it's arc sine, we are going to have an angle that's between negative pi over 2 and positive pi over 2. That's the output of arc sine. Since the value is positive, I know that the angle must be somewhere in quadrant 1. So I'm just going to sketch some angle in quadrant 1. Here is the angle that we're working with. So again, this is equal to theta, which is this angle. So if we know that this is the angle and we know that the sine of this angle is 1 over 5, that means that the opposite side length is 1 and the hypotenuse is 5. And then we could do a little Pythagorean theorem to help us find this missing side length. So it's going to be the square root of 24, which is 2 root 6. So again, we're just saying that arc sine of 1/5 is just this angle. So from here, we're just finding the tangent of that angle, which we defined up in our picture. And we can see that the tangent of this angle is 1 over 2 root 6. So that is our answer. All right, let's try one more together. So here we have the cosine of the arctangent of 3 over 8. So again, let's remember that this is just some angle whose tangent is positive 3 over 8. We know that since it's arctangent, it must be an angle between negative pi over 2 and positive pi over 2. Since this value is positive, again, it must be some angle in quadrant 1. So I'm going to call that expression theta. So we're just finding the cosine of theta. Now, if the arctangent of this angle, if the arctangent of 3 over 8 is theta, that means that the opposite side length is 3 and the adjacent side length is 8. So that means that our hypotenuse is the square root of 73. So now we're just finding the cosine of this angle. So the cosine of that angle would be the adjacent over the hypotenuse. So 8 over root 73. So again, you can see how important it's going to be that you know and really understand the domain and range of our inverse trig functions, because it really helps us determine which quadrant we're working in and what our answer will be. Okay, so the last thing that we're going to review is solving trigonometric equations. So when you're solving trigonometric equations, there's a few different methods or techniques that we might use. We are going to, and we'll do an example of each type. So a really common thing to do is just to try to isolate your trig function if you can and then finish solving. Sometimes you can factor your expression or your equation and then you can solve using the zero product property. Sometimes you will have more than one type of trig function in your equation, and if you can't factor, you may need to use a trig identity or formula to rewrite it. So if you can find a way to turn two types of functions into a single type of function, it might make the problem easier. And you can see here below, I have a bunch of the identities and formulas that you learned in pre-calculus. These can also be found on your little calculus reference sheet. So definitely make sure you have that handy as you're working through these. And then another really common thing to try if you ever get stuck with these types of problems is try squaring both sides and then maybe employing one of the methods above. But again, here is just a quick snapshot of the different formulas or identities that you can use. But again, you have these all on your reference sheet. All right, so let's give one of these a try. So here we have 4 times the cosine squared of x minus 2 equals 0. So we want all solutions from 0 to 2 pi. So here we just have a single trig function, so we can actually try to isolate this and then finish solving. So we have cosine squared equals 1/2. So we add the 2, divide by 4. And then here we actually can take the plus or minus square root of both sides. Square root of 1/2. So this is the plus or minus root 2 over 2. And again, don't forget that plus or minus. So from here, we can really just finish solving kind of just using logic. So we're wondering which angles have the cosine whose value is root 2 over 2. And since it's plus or minus, we are really looking for the angles in all 4 quadrants. So we actually are going to have 4 answers here. So we have pi over 4, that's our answer in quadrant 1, 3 pi over 4, 5 pi over 4, go, and 7 pi over 4. So just remember when you are working with cosine and the result is root 2 over 2, the reference angle is pi over 4. So it's extremely important that you really know those values from your unit circle, the angles and the values that go with them. All right, let's try another one together. So here we have root 3 times the tangent of x over 2 minus 1 equals 0. So I know that we do see the tangent of x over 2, but we can actually isolate and solve and then deal with the x over 2 kind of at the end. So let's try to isolate our trig function as much as we can. So I'm going to add 1 and divide by root 3. So the tangent of x over 2. I'm going to just rewrite this as root 3 over 3 just because, again, it might look a little more familiar. So here, since it's tangent and our answer is positive, we're going to be working in quadrant 1 and quadrant 3. And since it's tangent and the value that we get is root 3 over 3, we know that our reference angle is pi over 6. So we can say x over 2 equals pi over 6. That's one of our answers. We can also say x over 2 is equal to 7 pi over 6, which would be our angle, our answer in quadrant 3. And then you can see here that we can finish solving just by simply multiplying our answers by 2. So we get 2 answers here, x equals pi over 3 and 7 pi over 3. So again, if you have additional operations within your trig function, you could still solve by isolating and then kind of deal with those extra operations at the end, and you'll still end up with correct answers. All right, let's try example 8 together. So here we have 2 times the sine squared of x minus 13 times the sine of x plus 6 equals 0. So here we can't isolate our single trig function because, well, here we have sine squared and here we have sine. So we have to try a different method. And this one we could actually try factoring. So this would be considered maybe a quadratic type problem. I know that it's not a quadratic equation, but we can factor it as though it is. And even if we want to, we can try doing some substitution to make it a little bit easier for us. So let's say that I substitute u with sine of x. That gives us the equation 2u squared minus 13u plus 6 equals 0. So now you can see that this is a quadratic equation, which you should be able to factor. So we have 2u minus 1 times u minus 6 equals 0. And then from here, we can substitute back in. So here we have 2 times the sine of x minus 1, and then sine of x minus 6 equals 0. And then we can solve this using the zero product property. So we'll set each factor equal to 0, and then we can finish solving. All right, so here we have the sine of x equals 1/2. So there are 2 quadrants where sine is positive. So we know that we're going to have an answer in quadrant 1 and in quadrant 2. And we know that our reference angle here is pi over 6. So we get pi over 6 and 5 pi over 6. And then here, this actually is undefined. There are no angles whose sine is 6. So remember, the range of sine is -1 to +1. So this doesn't give us any answers, so we just have the 2 answers, pi over 6 and 5 pi over 6. All right, so here in example 9, we have 1 plus sine of x equals 2 times cosine squared of x. So again, we can't isolate because there's 2 different terms with our trig functions, and you'll notice this time this is a cosine function and this one is sine. And so we can't really do any factoring. There's no way to factor this expression. So we're going to ask ourselves, is there some way I can rewrite this using one of our formulas or identities? So we can actually rewrite cosine squared in terms of sine using our Pythagorean identity, sine squared plus cosine squared equals 1. So we know that cosine squared is 1 minus sine squared. So we can use this form of our Pythagorean identity, and we can actually substitute for cosine squared. So we have 1 plus sine of x equals 2 times 1 minus sine squared of x. And then we can try to see if there's a way to factor this one. So we have negative 2 sine squared of x plus 2. So let's move everything over to the same side. So to fact this, we could do substitution again, or you can kind of jump straight to the factors if you're comfortable doing this. So we have 2 sine of x minus 1 times sine of x plus 1. And if you multiply this out really quick, you should get what we have above. And then this, we can finish solving using the zero product property, like this. So we have the sine of x equals 1/2 and sine of x equals negative 1. So these are the same answers as that previous example that we just did. And then here, there's only one time between 0 and 2 pi when the sine of an angle is negative 1, and that's at 3 pi over 2. So we have 3 answers to this equation. All right, I have one last one for us to try together. So here we have cosine of x plus 1 equals the sine of x. So here, again, there's no way to isolate. We can't factor. We actually can't even rewrite one of our expressions in terms of the other. So we kind of have to resort to our last method that we talked about, which would be squaring both sides of our equation. Just be careful that when you do square both sides that you're squaring the entire side. So remember, this actually means cosine of x plus 1 times cosine of x plus 1. So make sure, again, you're squaring the entire side. So we have cosine squared of x plus 2 cosine of x plus 1 equals sine squared of x. And now, again, we're going to try to factor, but first I'm going to ask myself if there's some way that I can rewrite this sine squared in terms of cosine to match my other two. And we know, again, from that Pythagorean identity that sine squared, is 1 minus cosine squared. So that's a form of our Pythagorean identity. So I'm going to substitute this here. So we have cosine squared of x plus 2 cosine of x plus 1 equals 1 minus cosine squared of x. Let's move everything to the same side. So 2 cosine squared of x plus 2 cosine of x equals 0. And then I'm actually just going to divide both sides by 2. Or you could factor it out. Either way is fine. And we can factor this further. Cosine of x times cosine of x plus 1, GCF of cosine of x. And then we can just finish solving using the zero product property. So when cosine of x is equal to 0 and cosine of x plus 1 equals 0. Okay, and again, we only want the answers between 0 and 2 pi. So this one is going to give us pi over 2 and 3 pi over 2. And this one is when x is pi. So we have 3 answers for this equation as well. Alrighty, so that is all for our video today. Thank you so much for watching.